Okay, so let's take a look at WebAssign 6.1. You said you had a question about,
The interval notation specifically?
mm-hmm, okay, okay. Which problem are we looking at?
Number 8?
It's interesting because did you notice number four actually could be, interval notation, even though they wrote the definitions rather than the interval notations? Did you notice?
Yes.
They're,
Yes.
yeah, they're declining to use interval notation there. Um, but yeah. Oh, number eight. That's a fun one. Okay. So, can you see this okay? I mean, we'll tune into this in a minute here. 6.1, number eight. But it's an interesting interval, isn't it? Because V sub I is square bracket negative 1 over I to 1 over I square bracket, isn't it?
Yes.
Now, did you have any issues understanding what those sets actually look like?
No, I understand that this is us. Okay, so the no, I didn't have a problem understanding. At least I think I didn't.
Okay, good. So, let me just make sure this is in focus. So, you know what these sets look like. Let's just take a look. Maybe what is V sub one, for example, when I is one?
When I is 1, it's negative 1 over 1 to 1 over 1, all inclusive.
Hmm. Which is really just, the closed interval from one to one, right? And when
Yes.
I equals two, what is V sub two?
It is negative 1 over 2 to 1 over 2, all inclusive.
Hmm. And as I think it goes up to what, three or four in terms
4.
of the finite sets that we have to look at. Negative one third to one third, and what, negative one fourth to one fourth.
That's right.
And these are interesting because they are nested. If we draw a picture, here's zero. I'm going to draw it kind of big because things, start to, right, tuck into one another. This entire interval that's too wide is V sub one.
We're moving from the largest value toward the smallest value.
That's right, because it kind of splits things in half. So for V2 only goes from negative one half to positive one half. So V2 is tucked, inside V1. And then V3, of course, goes from negative one third to positive one third. So it's tucked in, you know. And then of course V4 is from here to here, from negative one fourth to positive one fourth. Okay. So you said you were having some trouble maybe with the interval notation solutions.
Yes. So it asks us a couple questions, the union, the intersection for the set, and I thought I was right to say it was negative for the union, negative 1 over 1 to, oh my, okay, I wrote negative 1 over 1 to 1 over 4. It should be negative 1 over 1 to 1 over 1 for the union.
That's right. The union from I equals 1 to n of the V sub n. Yes, it is V1 because, of course, all the other ones are tucked inside V1, right? So it should be negative 1 to 1, or you could say negative 1 over 1. to 1.
Whereas the intersection would be negative 1 over 4 to 1 over 4 inclusive.
Well, does your problem E say the intersection from 1 to 4?
Yes,
Okay, it's not from 1 to N. D is not from 1 to N, it's from 1 to
no.
4. Okay. So
There
what,
is one, oh, I'm sorry.
well, what number are we looking at actually?
We're looking at 8.
No, I mean B or C or D. I'm
We
sorry.
just we just looked at A and now we're looking at B.
Oh, okay. So this really is just from 1 to 4.
But there is another question that has N and it has infinites.
Yeah, yeah. Okay. So yeah, the intersection so A was from the I equals 1 to 4, and B
Y
was from I equals 1 to 4.
yes, there's D
This should
through
be
G
this should be
and
DI.
that's N and
Hmm.
infinity.
Okay. All right. So you're okay with B then?
Yes.
All right. And C is the union.
Yeah, no, C is j definition,
Oh, okay.
mutually disjoint.
And of course they're not. In fact, they're about as far from mutually disjoint as you can get, aren't they?
Yeah.
Because they all have something in common with one another.
Yes.
Yeah, and they all would need to be empty. So, they're not mutually disjoint. So what's the one that you would like to so you sorted out A, was there an issue with any of the other ones?
For well, for F and G, these are the infinites. And I looked at the class notes and the notation that you used for intersects and unions for infinites. And it has several, so it is, the intervals are, okay. Yes, for 1 to infinity, it would be inclusive 1, but then it increments and then it has another union symbol and another range, I suppose, or interval. Oh, yes, yes, yes. I see on your screen.
Yeah, I mean, let's just think about what it means to keep going forever. It just means, hey, it's V1, union V2, union V3, union V4, but don't stop at V4. Just keep on going. And of course, for the union, once you get the drift that this is the biggest set to begin with, and all these other sets are subsets of V1, the union isn't really that hard because it's kind of the same idea that we had when we looked at the union of V1, union V2, union V3, union V4. They're all contained in V1. So the union is anything that's in any of them. And that would be, well, V1's the biggest one. That same idea holds when we're looking at the union from I equals 1 to infinity, isn't it?
Yes.
Right? So what would be the union from I equals 1 to infinity?
V1 union to V infinity.
Right, but as an interval,
Oh, it would be inclusive V1 to exclusive well, inclusive 1 to infinity. Oh,
no,
negative.
no, doesn't go off to infinity. V1 is the biggest set, and it's bounded by -1 below and by +1 above.
Oh, we're still talking about the same set.
Yeah, these are all the same sets.
Oh, when I saw the infinity, I thought we weren't talking about the previous set.
Nope, these are all for this particular definition. The
Oh,
whole problem 8 is about sets that look like this.
I see.
Okay,
So,
how?
so even though the union is to infinity, we still have the same.
Right, because look, here's the biggest one is the first one. Union this one, but everything that's in this one's already in this one. Union this one, union this one. Doesn't matter if you keep unioning forever. The union is anything that's in any of them, and that starts out to be the biggest one to begin with.
Oh,
Does that make sense?
it does. I guess I,
You, that's okay. It's all right. I mean, it's new. I mean, that's the whole point is to kind of stretch our minds with notation.
wow.
You're fine. But let's think about the intersection is actually, I mean, do you understand? Do you understand why?
I
Doesn't really
understand.
matter how many you union together. The minute you've got V1, all the other ones are subsets of V1. So unioning V1 with any of these doesn't give you anything that wasn't already in V1 to begin with.
I see. So that infinity symbol above union is,
Which
see, I
means
autom
keep on going forever.
I see.
It,
Okay.
it's not,
Okay.
okay. So let's look at what it means as far as plugging infinity in to this. Okay, because that's kind of what's going on. I see where you're going with this. All right. So there's our VI. The union. So for part F, the union from I equals 1 to infinity of the VI. Okay. So um, even though it doesn't end, okay, there is sort of an abstract idea. Oh, three. That somehow when we take the union of these, this infinity is a concept. So, it's minus 1 to 1 union, minus 1/2 to 1/2 union, minus 1/3 to 1/3, close bracket, union. If you wanted to think about what it means to plug infinity in for the I here and infinity in for the I here, what's happening there is we're saying I gets huge. I just gets bigger and bigger and bigger. So in fact, we're dividing 1 or -1 by a huge number. Well, 1 divided by something huge, just think about it. 1 divided by 100 is small. 1 divided by 1,000,000 is teeny tiny. 1 divided by a gazillion is infinitesimally small. In fact, this starts to be very close to just being 0. And so does this. As I gets large, 1 over I approaches 0. Does that make sense?
I understand now. I was completely misunderstanding the direction that the values were increasing. I
Right,
I
right.
got
Okay.
confused because of the summations and the multiplications. Okay.
I know, right, right. But good. But this one's a little interesting when we start intersecting, then we really do need to start thinking about what happens, in the limit way out here, V sub, 10 to the 100 million, Like what is that? Because when we're taking the intersection, we're starting with from -1 to 1, but then we're going to intersect it with something that's inside of that. So the intersection, of course, of just these two is V2. But if you keep intersecting with smaller and smaller sets that are nested in between, just imagine what's happening. These sets are getting smaller and smaller and smaller until, way down the line, when I is huge, we're talking about a teeny tiny set that's really close to 0 on either side. But no matter which set we take, the next one is even closer to 0. And then the next one is even closer to being around, just teeny tiny interval around zero, to the point that the only element that's actually in all of these guaranteed is just the number zero.
Wow.
Because no matter, 1 over -1 over like, a million, 10 to the, or a Google, right? To 1 over 10 to the 100, I mean, it's like that's the largest named number we have, a Google, 10 to the 100. This is so tiny, but then there's even another one that's even tinier, the next one, -1 over 10 to the 100, and then the whole thing plus one. The point is it just gets smaller and smaller and smaller to the point that the only number that you're actually guaranteed is going to be in all of these is the number that is right smack dab in the middle, and that's zero. That's the only number that's not going to fail to be in all of them, no matter how tiny they get. Like, because all these numbers out here, well, they're not in here. So, like this number out here isn't in V2, so it's not going to be in the intersection. Any number in V2, well, it's not in V3, so that number's not going to be in the intersection. Any number you pick out here in V3 that's not in V4 won't be in the intersection. And if you just keep, just expanding with your microscope and looking closer and closer, the only thing that's left would be zero. It's actually
Wow.
guaranteed to be in all of them. So this was just kind of just a fun kind of mental exercise, a mind bender, so to speak. Okay, so other questions? Hey,
I
Sydney.
had a, oh, I'm sorry.
Go on. It's okay.
Oh, I had a quick one about partitions.
Sure.
Do, um, as an extension of indexed sets, for indexed sets, as the value of I increments, we move in all of the sets with the same value. So if it's like a set A, set B, at index I, both A and B have the same index value, and that's I, right? Or I'm asking.
I'm not sure I understand your question. We are given the definition of a partition. And because we just have to pick some letters for the definition of a partition, in order just to talk about the concepts, I mean, we can't write 100 different definitions. If I'm understanding what your issue is your issue that sometimes we apply the definition of partition when we don't have A sub 1 and A sub 2, but we might have B sub 1 and B sub 2 and B sub 3? Is that what you're saying? Or no?
Well, I don't know, because I'm asking about, so for a universal set to be partitioned, do each of the the subsets have
Uh-huh.
to have consecutive values like 1, 2, 3, and then 4,
Oh,
5, like that?
that is a great question. No, they don't have to. Um, they don't have to, but usually when we're trying to figure out a partition, we try to figure out some kind of numbering scheme for those sets that are called the partitioning sets. Actually, let's just look at the definition. Given a set a collection C equals A1, A2, for a finite partition, let's just say A sub K, of subsets of A is a partition of A if, and these sets right here These are called the partitioning sets. They do the work of partitioning A. And there could be an infinite number of them, okay? If, 1, 2, 3 things happen, but each AI is not empty. They are mutually disjoint sets, if you take any two of them that are different, their intersection is empty. If I isn't the same as J, in other words, if we take two different ones, that means their indexing numbers are different. You would not ever have the same set be labeled as both AI and AJ. I don't know if that's your question, but any one of these has its own specific indexing number. I mean, we do not generally skip around with indexing numbers. We decide which one is going to be A1, and we decide which one is going to be A2, and so on and so forth. I'm not sure if that's your question. And then, there is usually some kind of method to the madness of labeling the partitioning sets, but there doesn't have to be. I mean, is there a specific example that we could look at that could help me understand what difficulties you're having or try to get a better handle on what you're actually asking about?
Number 10 in WebAssign.
All right, that's great. Let's take a look at that. Okay, so here that we're not even given names for the different partitioning sets, like in part A, we're just given 3 subsets of this big set. So the set big A has little a, B, C, D, E, and F in it, okay? And they're not naming this subset A1, but you could do. We're not naming this subset A2, but you could do. Like if we were going to name these subsets, I would call this one A1 just because it's listed first. I would call this one A2, and I would call this one A3. All right. Does that help?
Yes.
All right. But the more intuitive way to think about this, and this is a good problem to help us think intuitively, is as we look at this collection of subsets of this set, what we're really going to be doing is this. Each element of the big set, okay, this is the set we would call big A. So little a, B, C, D, E, and F. Each element has to appear in exactly one of these partitioning sets. If there is an element that doesn't appear in exactly one of these, then it's not a partition. So let's first check the element little a. It needs to appear in exactly one of these 3 supposed partitioning sets. All right, so there it is, and it doesn't appear in any of these other ones. So far, so good. Then we check the element B. Okay, so it's in this set. So far, so good. It appears in exactly one set. Let's look at the next element, C. Does it appear in one of these sets? Exactly one of these sets. It appears there. Let's check D. Uh-oh. D appears here and appears here. And that means that the intersection of this set that has A, D, and E in it with this set that has D and F is not empty. There's an element that's appearing in 2 different of these subsets. That makes it fail to be a partition, because each element of the big set A has to be in exactly one of these subsets. And D is in 2 of them, and that means that the property 2, where AI, let's call this A1, intersect AJ, let's call this A3. So A1 intersect A3 is not empty. There's an element, namely D, that's in both of those, and that makes it not a partition. Does that help?
Yes, I see. So it doesn't matter the order of the elements in relationship to the universal set. It's that each element is unique in the set, and it's not
Right,
okay.
right. And so this is better actually than I think in my measure two material, I might have kind of gone overboard with putting the elements in some kind of order, didn't I? In the measure two material?
Yes.
I maybe made a mistake with that. Um, so it's kind of doesn't really matter what you do. There's always something that's going to go wrong, you know. Uh, I didn't want somebody to miss something because they were expecting them to be in order, but they certainly don't have to be in order. But the idea is that every element of the big set needs to appear in exactly one of the subsets, right? And, you know, if anything is missing, you know, you can kind of do a quick scan. Looks like everything is good with the second one. You know, none of these three sets share anything in common, and every element in big A, this set, does appear in exactly one of these. You know, that's the third part is that the union of these three sets has to be the big set. And it is. Nothing's missing. Like that's one of the things that could go bad, you know, besides what went bad here in part A was, oh, well, every element in this set with little a, b, c, d, e, and f. Yeah, every element does appear in one of these subsets. So the union of these subsets is the set big A, but we have a non-empty intersection between two of them. Here, nothing goes bad. Here, I think a couple of different things go bad.
Yeah, 4 is there twice.
Four is there twice. Is there anything missing, or does every element appear at once? No, every element does appear once. There's 1, 2, 3, 4, 5, 6, 7, 8. I thought this might have gone up to 9. So, so because 4 appears in two different subsets, it's not a partition because
Ah,
these two subsets aren't disjoint. You could call this subset A1. You could call this subset A3. A1 intersect A3 is not empty. What about this one?
I think 6 is missing there.
I think you're right. I see 1, 2, 3, 4, 5, 7, 8, 9. Yeah, the 6 is missing. So when you take the union of these three sets, you don't get this entire set. So it doesn't satisfy property 3. And none of them, I don't think that they're going to give you any examples where one of the sets is actually an empty set. You know, they're either going to make this go, because that's almost too obvious. You know, if they make one of the subsets an empty set, it's almost too obvious. But, you know, either you're going to have non-empty intersection or the union won't be the whole thing. But it's interesting that you say, you know, about doing things in order, because we looked at an example, and I kind of like this example. Find a partition of this set that has infinitely many subsets of A in the partition.
Wow.
It's kind of fun to play the game kind of on an infinite scale. Now, these are real intervals. like from 0 to 1, that's got infinitely many real numbers in it, right? That's 0, 1, right? But then we could say, oh, okay, now I'm going to pick up right where we, square bracket here. That could be one of the partitioning sets. And you could say, okay, I'm just going to keep doing this.
So if you continue like this, then you'll have an infinite set of, I want to say, one value increments.
Yeah, these are almost, in some sense we call these unit intervals because they're all length 1, even though it's kind of hard to imagine that we can measure a length when we don't have an actual upper, value, upper bound. We have an upper bound, but not a maximum. But yeah, if we define, you know, from I minus 1 to I, if we call this, the interval, A sub I, and this can be for I equals 1, 2, 3, just keep on going forever. Then the collection, which is the set of the A sub i's, does partition the non-negative reals. Like just there's an infinite number of these, right? And they each kind of look the same, but you just keep shifting over one and shifting over one. And there's no space between them, right? Like but they don't share anything in common. They don't have anything, even if they're sitting right next to each other. Certainly if they're not sitting right next to each other, if you take this one here and this one here, they surely have an empty intersection. But because we're putting a square bracket on one end and a soft bracket on the other end, even these intervals that are right next to each other have an empty intersection, right? Because the one is part of the, this set right here, but it's not part of that set right there. If you take the union of all of them, these just keep going forever. You get the whole non-negative real number line. So this would be an infinite partition of the non-negative
Oh.
reals. It's kind of a fun game.
And that union, that partition would be zero inclusive to infinity,
Uh-huh. Yeah,
exclusive.
the union from I equals 1 to infinity of the A sub i's would be exactly our A.
Ah,
I numbered it so that we could start with I equal 1 because 1 minus 1 starts us at 0. So this would be A1. This would be
I see.
2. Did I have to do it that way? No. I could have defined it from I to I plus 1, and started the indexing with 0. You don't have to start your indexing at 1 when you're doing partitioning. You could start your indexing at 0 or you could start it at 4. It just depends upon what makes sense. But when we make the definition, I don't want the definition to be unwieldy. Like, a highly technical definition would say this first indexing number wasn't actually the number 1. I would say this first indexing number is n naught. And this next indexing number would be n naught plus 1. And the next would be n naught plus 2. You see what I mean? And it just gets kind of unwieldy. So I would just say the definition. Well, the point is you've got some indexed sets, or at least some different sets. Basically, we're using the indexing just to indicate that these are different subsets more than anything else.
Uh-huh.
But we do generally try to tie the indexing in with the name of the set if it makes sense to do so. But in those problems that we just looked at in WebAssign, it doesn't really matter what you call the little subsets. Doesn't matter if you call them A, B, C, D, or if you call them A1, A2, A3. It doesn't matter. The point is you've got, some different subsets, and you just want to see if everything in the big set A appears in exactly one of those. Every element of A has to appear in one of them so that the union of those subsets will build A back, but you don't want anything in A to appear in two of them because then this property too would fail.
Okay.
And the reason we have this first caveat that we don't want any of them to be the empty set is because, well, if we let some of these subsets be the empty set, we could have a whole bunch of them be the empty set, and you're not adding any value. The empty set doesn't help you build A. There's no element of A in the empty set. See what I mean? So this is almost just sort of a technicality so that things don't get ridiculously silly, where you wind up with a partition that's got 100 empty sets as subsets. Technically, the empty set is a subset of A, but it doesn't help you build A, if you know what I mean, when you take the union.
Right.
So, this is more just a technical kind of don't do something silly.
Uh-huh.
It's very similar to the technicality that we have when we look at standard factored form of, if you remember, a standard factored form, it's or unique factorization. It said, oh, if you've got an integer n greater than or equal to 2, then we can write it as a product of powers of primes in a unique way. And the reason that we demand that these exponents are strictly positive is because otherwise we could throw in a bunch of primes that aren't actually factors of 100. If we let, you know, e sub 1 be 0, then we could say 4 equals, well, let me put it this way. We could say, let me just say e sub I. If we let e sub I equal 0, we could say 14 equals 2 to the 1 times 3 to the 0 times 5 to the 0 times 7 to the 1, which is silly, right? We don't want to allow 3 to the 0 or 5 to the 0 to appear as prime factors of 14 because they're not factors. See what I mean? So we don't allow the exponent 0. We don't want this.
That's really interesting.
We don't want P2 to be 3, and we don't want P3 to be 5 because they don't, So the idea of the empty set is similar in set land. We don't want, the collection to be like the empty set, the empty set, the empty set, and the set containing A, B, and C, and the set containing D and E, We don't want that. It's silly. But it's something that we have to actually say we don't want. I mean, the reason we don't want it is because it would be silly. That's not silly to say we don't want it. We say we don't want it because it would be silly to let it happen. Yeah, there are interesting things like that pop up in mathematics where we have to kind of carefully think through our definitions so that we kind of get the game going that we actually want to play.
That's really interesting.
Do you have some others? Can I help with some other problems that you looked at? Or did
Um,
you?
I I feel like I understand the measure two material. Maybe I shouldn't say that. I shouldn't be so bold.
Well, I think I better put some solutions up for you early this week so that you can just double check. How about I
Okay.
try to help out in that respect?
Yeah, that sounds good. it has a lot of indexing questions like the ones we were talking about.
And it would be helpful
And
to see the solutions to those, wouldn't it?
yeah.
Are there any specific ones you would like to look at now that you weren't sure about, or do you feel pretty good?
Um, it would be great to look at maybe number one, just or number two looks pretty, doesn't look, number one, just because the indexing is throwing me off a little bit, but I think that it's just substitutions like we've been doing with the proofs by inductions and the the multiplicative and the summations where we just take the index
Uh-huh.
value and plug it in.
Oh yeah, let's take a look at number one. Okay, so can you see okay? Because I'm actually looking at number one in the
Yes.
special homework section 6.1. So this is centered okay?
Yes.
Okay, so number one, yeah, this is an interesting little take on sort of a combination of what we did in class and the WebAssign, where I'm trying to use, um, a fraction. So, so it's very similar to what was going on. Um, and it really helps to draw a picture. But I think that the first question is, the union from what, I equals 1 to 4 or something. I mean, K
Yes.
1 to 4. So why don't we just take a look at what A1 actually is? What is A1?
A1 is negative 1, minus 1 over 1, 1 plus 1 over 1.
And if we simplified that, what would that come out to be?
That
What's
would be negative 2 to 2,
good?
inclusive, non-exclusive rather.
Exclusive. Nicely said. Good. And then what is A2?
That would be negative 1 minus 1 over 2, comma 1 over 1 plus 2. Yeah, 1 plus 1 over 2, excuse me,
I'm with you.
is negative 3 over 2,
Hmm.
comma 3 over 2,
Great.
exclusive.
Yeah. And the game just kind of keeps going, but it's going to help us if we actually look closely. And if, it's also very helpful if you actually understand fractions to some degree. And for students who don't, gosh darn, it's certainly high time to understand what fractions mean. Let's just draw a picture. We don't need to go past 2 or -2, do we?
No, our values are getting smaller, I believe.
Exactly. And none of them are going to be smaller than -1 to 1, right?
Right.
I'm going to just off center it a little bit. I want a little bit more room. But like we're never actually going to get inside -1. It's always going to be -1, minus a little more, and
Mm.
1 plus a little more. No matter how big K gets, we're never actually, you know, it's going to get really close to being -1. But, right here, -3/2 is here, and 3/2 is here, right? So that one is inside A1. A1 is the big one. But then -4/3, well, it's a third more, right? So it's like here and here. So, from 4/3, -4/3 to +4/3, and then halfway, I guess it's like right there would be -5/4, and then like right there to 5/4. It's hard to, But the point is, they're nested this way. So this is the smallest one. That would be the intersection. This is the biggest one. That would be the union. If you're taking the union from I equal or K equals 1 to 4, you'd get the whole shebang exclusive. You take the intersection, you just get from K equals 1 to 4. You get these. But, again, if you talk about going all the way to, 1 over, I don't know if I ask about n, but I think I just jumped directly to infinity, right? The union.
Yeah, so number 3 for C and
uh,
D, there's infinity. But
yeah,
can we talk about n? We didn't talk specifically about n.
we can do. N is just, we don't know what n is, but if K is n, we don't really know where it is, in terms of here. If n is getting big, we just imagine this is getting closer and closer and closer to being from -1 to 1. But, it's going to be -1 minus 1 over n, and then 1 plus 1 over n. And if we want to get a common denominator of n, right? Well, this is -n minus 1. This is n plus 1. But we can bring the negative out. It's negative n plus 1 over n to positive n plus 1 over n. You could think about it that way. And if you think about it, that's what's going on here. This is -2 over 1. This is -3 over 2. This is -4 over 3, 5 over 4. Right, the numerator is 1 bigger than the denominator. 3 halves, 4 thirds, 5 fourths, n plus 1 over n.
Mm.
So you see what I mean? Like that, I mean, you don't have to write it like this, but if you look for the pattern, these become fractions with the numerator being 1 integer larger than the denominator, with a -1 and a +1. But you could just leave it like this. I mean, the point is, as n gets big, 1 over n heads to 0, right? As n goes to infinity, 1 over n goes to 0. That's kind of one of the basic things we start to learn in calculus as n goes to infinity. 1 over n, this just, because 1 over something huge is really tiny, and the huger the denominator, the smaller the quotient, 1 over that huge number. So as n goes to infinity, 1 over n goes to 0. So the only thing that you're actually guaranteed that's going to be inside all of them is actually going to be from -1 to +1. 1 and 1, -1 will be in all of them because they're all going to be -1 minus a tiny bit more. So -1 will be on the inside. See what I mean? Like no matter how close to -1 and +1 the open endpoints of A sub n get, in other words, no matter how big n gets, this is still a teeny tiny quantity. It's getting close to 0, but it never just disappears. And even if it did, the negative, yeah, it never disappears. So the -1 is always still part of the set. So if we took, the intersection forever, no matter how big n gets, this is always going to, even for n huge, the numerator is still going to be a tiny bit bigger than the denominator. And here too, in terms of absolute value, the numerator is a little bit bigger than the denominator. So this value is a tiny bit bigger than 1. So negative, this value is a little bit to the left of -1. This is going to be a tiny bit bigger than 1. So the positive value is just a little bit to the right of 1. -1 and +1 are always included in each one of these. So the intersection, interestingly enough, isn't soft brackets. The intersection is square bracket -1 to 1.
Wow. So you don't have to accommodate those changing slightly larger values because you're looking for the intersection.
That's right. Like, I mean,
Um,
the yeah, we don't really care about what's happening out here. We really care about, if we're taking the intersection, we care about what's happening, as we start to look at sets that are getting closer and closer and closer to being from -1 to +1. The point is, they all have this form. And even for very, very, very large n, this is still a teeny tiny bit bigger than one because the top is bigger than the bottom.
I see.
And this is right, and this is a little bit bigger in magnitude than one. So negative that is a little tiny bit to the left of -1. So the -1 is actually still included in the intersection. I guess I should put K. But these are the only, you're guaranteed -1 will be in all of them. You're guaranteed one will be in all of them. But there is no number to the left of -1 or to the right of one that would be guaranteed to be in all of them. See why is that, Lev? Like, let's say here. All right, so let's say here's one. Okay, and we're looking closer and closer and closer and closer. The minute you think that there's a number to the right of one that would be, in all of them, your best enemy just has to say, "Oh, you've picked that number. You think that's going to be in the intersection of all of them? But what about the one that's in here, that's to the left of that, And it leaves that point out. So there is no guaranteed point on the right that's going to be in all of these except one. See what I mean?
I see.
The minute you pick a point, then somebody will find an end that's big enough that the right soft bracket will tuck in to the left and leave that point out, and it won't be in the intersection of all of them, so it won't be in that big intersection.
I see.
And of course, the same thing happens
Interesting.
on the other side too. So it's just a little mind exercise. Um, you don't need to obsess about it or anything. I just wanted to see what people would do with it, and if anybody would be curious about why it is that way. I'm not going to make it worth a whole lot of points on a test or something, but it is interesting to think about, what happens if we try to abstract, uh, if we try to kind of see the geometry of it, what's the pattern, what's really going on.
I see.
Was there another one from the measure to material that you were wondering about?
I think number one kind of fits into this nicely. It wants you to give an example to prove whether or not two different sets are disjoint or not, and it has patterns.
Mhm. Um, are the sets in the collection mutually disjoint, right? The sets.
That's number one.
Okay, so just
I mean,
start.
I'm subsets. I'm sorry, not mutually disjoint, but is one a subset of the other?
Which problem number one in WebAssign?
Yes, 6.1.
Ah, thank you. Oh my goodness.
Excuse me.
Number one. Hmm. Oh yeah, that's a good one. Because they're talking about A being multiples of 5 and B being multiples of 20. Is that the one?
Yes.
Ah, that's a good one. Let's see. The set A is this is WebAssign 6.1, number one. Yeah, A is a set of N and Z such that what? Can you read the rest of it to me?
Such that n equals 5r for some integer r,
Okay,
and
and what is B?
B is the set M in Z, such that M equals 20s for some integer s.
Great.
And I thought they were both subsets because they're both factors. They both share common factors.
They do, well, they do sort of, kind of. Let's, let's, let's list some of the elements in A, shall we? Let's just take a closer look.
Right. 1, 5, where R equals 1.
Oh, yeah, well, and R is any integer, and it doesn't say whether it's positive or negative, right? So we'll start with 1. When R is 1, what is in?
5,
All right, keep going. What else will be in?
and then 10, 15, 20. But could we use 0 and negative
Yeah,
numbers?
yeah.
Ah,
So when R is 0, what is in?
0, n is 0, and then we'd have -5, -10, -15, -20, etc.
So in fact, if we wanted to kind of organize these thoughts, it'd be like -15, -10, -5, 0. These are multiples of 5, right? These
Right.
are all multiples of 5. Okay. Now what about B?
B is multiples of 20.
Okay.
Um,
So maybe
we-
we'll put 0 in the middle, right?
okay. And then -20, -40, -60, etc. And we'd have 20, +40, 60, etc.
So when in doubt, push pencil. Because there's a big difference between these and these. I mean, -20 is going to be in here, right? And we're going to get to -40 eventually, right? And we're going to get to 60 and 80, but -5 and -10 and -15 and -25 and -35, and they're not in B.
But isn't it enough to have -20 and 20 in both sets to make A a subset of B?
A is a subset of B. You have to go back and review our notes for subset means if X is in A, then is
Oh,
in B. In other words, if we
oh,
drew a picture, A as a set would live completely inside B.
oh,
And there are lots of elements in A that aren't in B.
wow.
It's false, right? Because 5 is an element of A, but 5 is not an element of B.
I
But
see.
everything that's divisible by 20, because it's divisible by 20, 20 is 5 times 4. M and B will also be in A because if M has a factor of 20, there's a 5 in the 20, but there's not a 20 in the 5, you see.
Ah, wow.
Here, B is a subset of A, since M in B means M equals 20R, but that equals 5 times 4R, so that equals 5 times S, and that's an element of A. So X in B implies X is in A. And that's exactly what it means to say B is a subset of A. We're going to start our discussion on Tuesday with to dig in more to this idea of subset.
Okay.
We're going to really, we're going to start to learn how to prove that sets are subsets of other sets.
That was really informative. Thank you.
You're very welcome. Have a
Mhm.
wonderful evening and thank you for coming to office hours.
You too, Professor. Thank you.
See you
Good
later.
night.
Good night.